Yeah, hi everyone. My name is Sung. I'm an engineer from Marketplace Platform, and I've been at Uber for 2 years and a half. So in this presentation, I'll talk about the work we do to make the storage and dispatch system reliable to ensure always-on experience for our users. So here's the agenda for today's presentation. So first, I'm going to lay out the background and talk about what reliable storage means. Then I'll present the storage system we built, focusing on how the system provides high availability and consistency in the face of various failure scenarios. And lastly, I'll close the presentation with some of the challenges we face and future work. So first, to put things in perspective, here's a brief history of how Uber's dispatch system has evolved over time. So in the beginning, the dispatch stack started with PHP-based system using flat files. And as Uber entered hypergrowth stage and saw exponential growth in traffic, it became critical to kind of redesign the system to be horizontally scalable. And because dispatch is stateful and transactional in nature, much of the scalability challenges we encountered had to do with storage. And as you can see in the chart, many of the iterations involve partly replacing the underlying data store. From flat file to MongoDB for persistence, MongoDB to Redis for speed, Redis to React for availability, and finally React to Cassandra for cross data center replication and operationally. So to motivate the discussion on what problem we're exactly trying to solve by reliable storage, I'm going to tell you about an outage we had a while ago. So exactly 2 years and 3 days ago from today, on August 21st, 2015, we encountered one of the worst global outages we had. So impact-wise, the duration of the outage was about 20 minutes, led to 46,000 trips being interrupted or aborted. So it was obviously a terrible experience for users. It flooded our ops and support with the tickets, and we spent a huge amount of effort with the refund. And needless to say, it was a financial loss for Uber. And for context, we were when the outage happened, we were in the midst of a major migration. So we were moving from legacy system running on Redis to a new system based on React. And in case you're wondering, React is a open source key value store based heavily on the Amazon DynamoDB paper, Dynamo paper. So, so the root cause of the issue was twofold. So basically, we saw a sudden increase in React sibling. So sibling is something we use to do the versioning and the conflict resolution because the React is the eventual consistent store. So the first one was the sudden spike in the siblings that led to the increased load in the system. And second, the second factor was just purely a mistake on our part because we didn't put any limit on the client connections. So basically, the increased sibling count led to errors, timeouts, and then the client basically started retrying. And because of the unbounded client connection pool size, the client basically requests kept increasing, and it eventually brought down the React. So if you see the graph on the right side, the first spike, so the first top graph shows the read latency on the client side. And then you see the first spike due to the sibling increase. And then as the client, the bottom graph shows the pending requests on the server side. And then you see the connection count increasing on as observed in the React. And then the read time in relation increases. And then it just, all the requests are timing out and bringing down the React. So here, the mitigation was just failing back to our old system that were running in Redis. And because there wasn't any syncing between Redis and React, we ended up dropping all the states for the 46,000 trips that were in progress. So the outage revealed many shortcomings in our system, some storage related and others more fundamental. First, there was no cross data center replication. So if you see, I mean, the issue only affected one data center. So if we had cross data center replication, then we could have quickly mitigate the issue by failing over traffic to the backup data center. And lacking that, we had to fail back to the legacy system, and it caused data loss, which is a no-no. Second, the failure domain was just too broad. The storage issue just affected all the cities in the entire single data center. And ideally, you should have just affected a subset of the cities in the data center. And third, there just wasn't enough service protection. So, like such as circuit breaking and load shedding. So, and which would have allowed the system to kind of run in kind of partially degrade mode as opposed to dropping entire traffic onto the floor. So the upshot is that the outage basically led us to kind of double down on our effort to make the system more reliable, including the storage. So just stepping back, what do we mean by reliable storage? So according to the Oxford Dictionary, reliable means consistently good in quality or performance, able to be trusted. So I think the three keywords here are consistently, quality, and performance. So I think in the context of storage, I think that the consistently here refers to availability. And some of the ways we can achieve high availability are through redundancy, replication, and having a small failure domain. And then the second keyword is quality. So besides the usual responsibility of the storage, like serving read and write requests, the storage has to ensure correctness and consistency. And as Brandon mentioned in his talk, sometimes we need to make kind of explicit trade-offs between the availability and consistency as captured in the CAP theorem. And last but not the least, the storage has to be performant, and it needs to uphold kind of the latency and throughput SLAs. So the post-mortem for the outage we had revealed kind of many gaps in the system, and it led to several follow-up initiatives. So the first was introducing the pods. So this is where what like spurred us to build a pod. So introduce the pods and to reduce the size of the failure domain. So technically, this is not entirely storage related, but it does have a huge ramifications on the storage architecture. So to understand why this is a case, we'll first take a deeper look at pods. So I think you saw this graph. So basically, this is high-level view of the dispatch system. There's just a lot of other systems that participate in core trip flow, but I'm kind of omitting them. So at the top is the mobile clients that talk to our data center through the API gateway. And then the API gateway in turn routes the traffic to the dispatch system here. And then the dispatch system is a collection of microservices, some stateful and some stateless. So the diagram here happens to just show two of the stateful services, demand and supply. So demand kind of captures the job state machine, supply the driver state machine. And so coming back to the pods, for the fault isolation, the dispatch system is split into pods, and this shows only 2, but in actuality, there are about 10 at the moment, and each pod is serving a subset of like non-overlapping cities. And then the API gateway here listens to the city pod mapping and is responsible for routing the request for a given city to the proper pod. And the pod can be scaled horizontally by adding more pods, but also we can scale the pod vertically by adding more instances to the pod. And moreover, we have 2 data centers to support. So, so pods reduce the size of the failure domain. So for example, here, if there's an outage in the west, we can, the outage can be mitigated by failing over the traffic to the east data center. And while it's not shown in the diagram, if the issue just affects one of the pods, we can fail over the traffic for that pod to the remaining healthy pods in the same data center. So that's a pod failover. So this failover is hidden from the dispatch services. So and they need not handle the replication explicitly. So for the most part, they'll continue to kind of read and write from the storage system, and then it is the storage system that takes care of the replication. And of course, like there's one exception, which is the API gateway, because it has to listen to the changes in the city pod mapping. So one thing that this diagram doesn't show is like how the states are replicated across pods and across data centers. And it brings us to the remaining follow-up items for the outage. So when we designed the pods, we actually wanted that pod isolation to apply even to the storages. So it'll be completely self-contained. And then the replication should support both the pod and the data center failover. So these are kind of more concrete requirements. And I'm using this term storage layer just and to clarify. I'm kind of using it like as opposed to like so storage layer is kind of abstraction as opposed to like data store or storage that's a specific implementation. So first, one of the requirement is that the system has to be highly available with 4 nines availability with multiple redundancy to prevent cascading failures. And achieving redundancy means supporting data replication and failover across pods and DCs. And for consistency, the system provides strong consistency within a data center, but eventual consistency across data centers is okay. And some of the other requirements are that the system has to be horizontally scalable, simple to operate and maintain, and support like a pluggable key value store such as Cassandra or some of the public cloud offerings such as Amazon DB or Google Cloud Store. So given the requirements, we have built a Marketplace Storage Gateway or MSG for short. So it provides KV APIs for single row and batch operations. The data model is schema free and expects a binary value type. And applications typically encode their data in JSON or Drift, but we kind of treat it as like a binary blob. And the storage backends are swappable, and at the moment it's powered by Cassandra, which is another NoSQL store. And then the reasons for moving away from React to Cassandra are primarily 2. So one is that the replication is not free in the open source React KV. And second, Cassandra is better supported and managed within Uber, and we want to kind of leverage all the support that the infra that Uber is providing for Cassandra. But more importantly, the system achieves higher availability than what a single Cassandra cluster can provide it by using 2 Cassandra clusters, which we refer to as pod and region cluster, respectively. So this diagram shows MSG as a part of the dispatch system. So there are 3 key components. So one is the MSG Gateway. So all the requests are routed from the application to the MSG Gateway. And then what the gateway essentially does is that it does the double read and double write to the pod and the region cluster. So like the pod clusters are like self-contained. So they're totally isolated from each other. And we were quite paranoid. So like we didn't enable any Cassandra application there, so that like any issues in one pod cluster doesn't somehow spread across other pod cluster. And in contrast, like we have the region cluster. So there's only one region cluster per DC. And for the region cluster, we enable the Cassandra application. So the region clusters are what enables the data to show up or replicate or be available in both data centers. So this is kind of the close-up view of the MSG Gateway. And as I said, the gateway does the double read and writes, and it essentially like maintains a connection pool to the pod and then the region cluster. And so the data is tagged with a monotonically increasing version. And for the conflict, so because we have like 2 clusters, and because you know, then the gateway is kind of responsible for keeping the data in sync. And so when the gateway does a double read from pod and region cluster, it basically checks for any discrepancy between the data between the 2 clusters, and resolves the conflicts by looking at the version. So like the resolution policy is like last right wins policy. So we basically we take the data with the larger version, and this is handled by the repair manager module in the diagram. And there are times when writes are partially successful, like, you know, when we're writing, like the write might succeed to the you know, pod store, but fail on the region store. And we when we have partial failures, we basically write the failed writes to the replay log backed by Kafka, and then we'll asynchronously replay them. So in this way, we can keep the 2 clusters in sync proactively, because without the replay, the data will be kept in sync only through the reads in lazy fashion. So replay log basically enables the data to be made consistent proactively. So given the pod and region, given the pod and region Cassandra cluster setup, I mean, there are certainly like many Cassandra clusters that we need to maintain. So there are like 10 pod cluster and 1 region cluster in 1 DC, and like having to operate these clusters manually would be a non-starter. So crucial to the design here is that the Cassandra clusters are managed by Cassandra Mesos, which essentially runs Cassandra as a service on Mesos and automates a lot of the node operations, like adding or replacing a bad node. And I think it was open source in collaboration between Uber and Mesosphere. And in terms of a consistency level, we use local quorum of replication factor 3 within the data center. And then the data between the data centers are replicated asynchronously. With Uber's data center, like the cross DC network latency P99 is about 50 milliseconds. So it means that the when there's a failover, there's potentially risk of reading stale data. But this is like a trade-off that we're explicitly willing to make, because if we were to write to both DCs every time for all the reads and writes, we will be paying like a heavy network latency penalty. So having looked at the system design for MSG, now we come back to some of the desirable properties of reliable storage, and we'll now look at how MSG and the combination of pod and region clusters are compatible with the pod topology we introduced, and how it helps with the failovers. So this diagram shows pod failover. So initially the traffic for the SF is going to pod 1, and for whatever reason pod 1 catches fire, and then we fail the traffic to pod 2. So you see the SF showing up in pod 2. And in the onset, the data for SF will be missing in the pod cluster. But recall that we always do the double read. So and the region cluster here will be having the data for SF. So so when the repair manager detects the discrepancy, it'll basically try to repair or fill the data into the pod cluster in pod 2. Similarly, upon data center failover, so we might do this upon power failure or cooling failure. So now with the data center failover, SF is routed to pod 1 in east, and again, like the region cluster, for the region clusters, we enable the Cassandra replication. So the SF data will be available in the east. So we again do the double reads, and then the pod cluster in the east will be repaired. So of the desirable properties, the other one is the correctness. And for the correctness, there is the consistency and transactions. And I think I kind of briefly went over the consistency about the consistency level that we set for the Cassandra and the repair module. So I'd like to spend some brief time on how we handle the transaction, because I think that's also quite important. So basically, there's no ACID transaction support in Cassandra or MSG, but a lot of workload for the dispatch is transactional and involves a lot of read, modify, write, and of course you can kind of model your like workload as a append only, but it has its own set of problems. So what I'm going to talk about is like, given that there's no transaction support in MSG, like what applications do instead to ensure transaction isolation. So for the single like NAD or single table transaction, so we try to scope the microservices such that like they're responsible for a set of NADs that do not require distributed transactions. So and because a single NAD transaction is like easier, can be like wholly owned by a single service, and that service doesn't need to coordinate with other microservices. So like in the diagram, like the supply service will be responsible for the transaction for driver state, and the demand service for the job state. And when the serializable transaction isolation is required, meaning that the where we want to guarantee that the no two transactions happen concurrently, we use either the application sharding with the in-memory locks. So this is what Brandon talked about, or the lock service. So I think like I see the application shard and in-memory lock combo as like every instance kind of acquiring a range lock. So it's like the load will scale with the number of instances, whereas like with the lock service, the load will increase with the number of rows. So it actually puts a lot of text on the locking service. But there are times when the distributed transactions are required. So like some operations might span like multiple NADs, and for like distributed transaction involving multiple rows, like multiple shards for distributed store, or even multiple tables, multiple like data stores, we use Saga framework. So Saga is based on the like the 1987 Saga paper by Garcia Molina, and you can kind of think of it as like a set of operations forming a workflow, and there be kind of external kind of transaction manager or workflow manager that's kind of that makes sure that all the operations all succeed or like they fail and or rolled back. And I think the key insight here is that the rollback or the cancel is not so much the DB level undo, but it's like application level undo. So like an example is like some service might actually send a push notifications to the client saying hey, the driver is assigned to you. The rollback or the compensation, the paper refers to compensation, it would be sending the driver the writer another push notification saying that, hey, the driver is no longer assigned to you. So there's a little bit of application semantics. And our implementation in Saga is a bit like a two-phase commit, more or less. So has a proposed commit and cancel. So basically, the service who would issue create Saga, or like you would issue a long-running transaction, and then the Saga coordinator will send the proposed to all the participating services, and if all the services vote yes, then the coordinator will issue a commit. But if one of the services say no, then the coordinator will issue a cancel or a compensation. So the topic probably merits another whole presentation, but I just want to I want to bring it up because it's quite interesting. So finally, I will just mention some of the challenges and problems we're actively looking at the moment. So philosophically, something that we continue to kind of pursue is like separation of concerns, and like making each layer of the system kind of wholly self-contained and easy to reason about. And a big focus of our current system, like the MSG, has been like, making sure like the data replication is handled transparently from the application, and so that the application doesn't have to be aware of the failovers when accessing data from the storage layer. But this is all good and well, but like the elephant in the room is really the transactions, because like the eventual nature of Cassandra, like some secondary indexes will be eventually consistent. When there are failovers, there'll be some inconsistent states, and the applications still need to do a lot of heavy lifting to kind of unbreak or recover from the bad states. And I think this is where like the kind of distributed transactional store that kind of supports ACID transaction semantics will help. And I think this is something that we're actively looking at in collaboration with the infrastructure team at Uber.